Yeah.
Hey, have you ever heard about the Laser Interferometer Gravitational Waves Observatory? Maybe you have. It's often called Ligo, and it's this huge project that was meant for the detection of gravitational waves. But if you have heard about this, you may ask yourself, what are these gravitational waves? Well, as we all remember, it was in 1905 that Einstein introduced his special relativity theory to the world for the first time. With this theory, we realized that space and time were somewhat related. Einstein's main idea was that all the laws of nature must be the same in every freely moving laboratory in the world, everywhere in the universe. If we take a look at Newton's law of gravity, we realize it takes into account an instantaneous distance between two observers. We already know that this will be different from an observer in Earth relative to one in the Sun. So Albert noticed there should be something missing in this equation. This led to the general relativity theory, where we forget the gravity as a force, and we now define it just as the result of the curvature of the geometry of the universe, which is caused by a mass, of course. So in this new way of dealing with gravity, a rather sophisticated branch of math is really useful named tensor calculus. As we will be dealing with curved space and time, this is very useful because tensorial notation allows us to write equations in such a way that they are invariant to any coordinate basis. Just for you to get a glance why this is so useful, let's have a quick review. In tensor calculus, a tensor rank 1 can be either a vector or a one form, which is really just a distinction between columns and rows. As in relativity we will be dealing with 4 dimensions, we use Greek letters to design from 0 to 3 coordinates. So we can write a vector as in this way, that it will be a column, and basis vectors, which are x, y, z in the Cartesian basis, can be written as a lower index, like this way, where space can be, I don't know, any curvilinear basis or a Cartesian one. If we use the Einstein summation convention, we notice we can write a vector in this way, where the coefficients will be multiplying the basis vectors. So what if we took the derivative? The total derivative would mean to differentiate partially each component, so we write it in this way. But we notice we will end up with a product rule. And so the derivative of a vector in this tensorial notation would end up as this. As you may have noticed, the partial derivatives of the basis vectors are already a vector, so we denote them with the Christoffel symbols, which can be read as the mute component of this partial derivative. And so, in this representation, we can see how deriving the basis vectors allows us to know how the geometry of the universe changes. Just as the waves in a water pump, almost any event could cause a disturbance in spacetime. However, the scale of the amplitudes of this wave reaching Earth is about 10 to the minus 20 meters. This is why we need really energetic and really massive events to occur for us to measure them. Also, unlike mechanical waves, gravitational waves transfer no momentum. But what they do is that they change the distance between two fixed objects, depending on the way the wave is traveling. It may happen in this way or in this way. It may happen that in a region of spacetime, the gravitational field is weak but not stationary. This can happen far from a fully relativistic source, undergoing rapid changes that took place long ago enough for the disturbances to reach the distant region under consideration. We may call this gravitational radiation or waves.
Now that we have defined what gravitational waves are, the real question is how can we detect it?
LIGO's twin interferometers are the engineering feat that allows us to detect disturbances in spacetime as small as 10 to the minus 19 meters. To understand how these interferometers work, we should first think in terms of the Michelson interferometer, since LIGO's operation is pretty similar to the interferometer used in 1887 to detect the ether.
The LIGO interferometer works in a similar way that the Michelson interferometer does. Here is a simplified illustration of how it works. The laser beam gets divided into two, and then each one travels the length of the arms until they reach the mirror, and this one reflects the laser beam back through the length of the arms. When they meet, they create a pattern of interference, and this is what the photodetector detects. When a gravitational wave passes through, since it is transversal, it contracts and expands the length of the arms, which creates a difference in the path and creates a pattern of interference. Here is an example of how the phase difference can affect the interference that we observe. The Ligo's interferometer is arranged in a way that when the lengths of the arms are the same, the pattern of interference is destructive.
In 1990, funding for the initial LIGO design known as iLigo was approved and its construction started. This model operated for 9 years without any useful detection until 2008, when it undergone a set of upgrades. The advanced LIGO, A-LIGO for short, started working in 2015, when after weeks of operation the first confirmed gravitational wave from a binary system of two spiraling black holes, 36 and 29 solar masses respectively, collided, releasing 50 times the power of all stars in the universe for a span of 20 milliseconds. The detection of a gravitational wave wasn't an event of luck, but rather a consequence of the fine-tuning of LIGO's ears. The engineering improvements between the noise reduction systems on iLigo and A-LIGO was the determining factor that allowed LIGO to listen to the ripples made by the colliding black holes 1.4 billion light-years away. But how can we reduce the noise from unwanted sources?
LIGO uses four main components to increase its sensitivity and get rid of unwanted noise: vacuum, seismic isolation, data collection, and optics. Because LIGO interferometers are extremely sensitive, they can pick up vibrations from even trucks driving nearby or earthquakes, so it's important to have a seismic isolation system. The LIGO has one, and it divides into two main parts, which is the active damping and the passive damping. The active damping consists in creating counter movement to the vibrations that are affecting the interferometer, and the passive system consists of a pendulum that eliminates all vibrations that weren't eliminated through the counter movements, so they act complementary.
Vacuum. LIGO has a vacuum that serves two main purposes: get rid of air and of dust
Optics
particles.
consists of
The problem
lasers,
of air
mirrors,
is that
and a
its molecules
photodetector.
can hit the mirrors and move them, masking the gravitational waves. Also, the index of refraction of the air when passing through the laser can change the apparent distance of the mirrors. On the other hand, the problem with dust is that it can scatter the laser light. The atmospheric pressure of the vacuum is 1 trillion that of air pressure at sea level.
The laser consists of a 200 watts that is amplified through 4 steps. In the first step, a laser diode emits a 4 watts beam of 808 nanometers. Then it goes to a non-planar ring oscillator where it bounces and then emits a beam of 2 watts and 1064 nanometers. Then it goes to the MOPA, which is the master oscillator power amplifier, which amplifies the beam from 2 watts to 35 watts. And finally, it goes to the high power oscillator that emits again the beam, but with an increased power from 35 watts to 200 watts.
Mirrors. They are made of pure silica glass and absorb just 1 in 3 million photons that hit them, which allow most of the laser light to be reflected. They also refocus the laser so that it doesn't spread out because of its multiple reflections, each weigh 40 kilograms, which avoid the laser to move them due to the law of inertia.
Computing system. It is in charge of both running the other instruments and of processing the data collected. This last process requires a vast computing infrastructure since LIGO collects terabytes of information every day.
So, as many similarities as LIGO's interferometer have with the Michelson one, it is also different because in order to detect the disturbances we want to measure, we need a very, very sensitive machine. And in order to do that, two main systems were added to the Michelson original idea. The first is these two little mirrors right here. These two little mirrors are known as Faury-Perot cavities. And what they are basically mirrors which allow the laser incoming from the beam splitter to enter the arm's length, and then when they are in this path, and they return from the mirror at the end of the arm, it reflects in such a way that the laser travels, instead of 4 kilometers that is the length of the arms, it travels 1,120 kilometers each laser until they meet on the beam splitter, and they emit us and they form the pattern. And why to do this? Because as we increase the length of the arm, we increase the sensitivity of the machine by amplifying the vibrations that are being felt. The other thing that is also added is something right here that is a mirror, and more appropriately it is a power recycling mirror. What this power recycling mirror is, it takes the 200 watt laser incoming from this part, and since it is a one-sided mirror, it allows the photons to enter the interferometer arm's length, which are positioned in a certain way that all the photons incoming from these arms get back to the power recycling mirror and then emitted again. So the photons incoming from the reflection and the photons incoming from the laser add up, and that gives more power, exactly 750 kilowatts instead of 200 watts that was the laser incoming. And that amplification in power, what affects is the resolution. We have a better resolution of the image, and thus we can detect better the little disturbances that a gravitational wave represent.
There are two LIGO detectors, one in Livingston and one in Hanford. However, there are also other observatories in the world, such as Ligo in Italy and Geo 600 in Germany.
Due to the highly sensitive nature of the interferometers, it is important to have many and widely spaced interferometers, because in that way we can differentiate between local noises such as earthquakes and other vibrations that local interferometers pick up, and gravitational waves that should be listened by all interferometers with a difference in timing, and that difference in timing can give us insight on how to triangulate the source on the sky, and also it helps us to determine the polarization of the gravitational wave.
On September 14, 2015, the LIGO detectors of Livingston and Hanford both detected a signal that appeared to be a gravitational wave. The frequency of this wave was from 35 to 150 Hz. The maximum strain, which is the difference of length between the interferometer's arms, was of 1.2 by 10 to the minus 21 at its maximum, which is a very small amount, but can be detected due to the high sensitivity of the interferometer. The event that caused the signal of the wave detected happened at a distance of about 1.3 billion light years. With information of, for example, the strain of the signal received and the frequency, we can compare it to mathematical models made based on the theory of general relativity to know what was the event that caused the gravitational waves. Also, with information about the difference in time between the signals received at both of the detectors, and also information about the wave polarization, we can estimate where in space the event took place.
The discovery of gravitational waves offers a whole new insight of the universe, because as we know, gravitational waves don't interact with matter in the way electromagnetic waves does. They remain basically the same along their path in the universe, and with this premise we can theorize stochastic waves, which are the remnants of the Big Bang Theory, an event of the measures we need for a gravitational wave to be detected. And this will give us insights on the first stages of the universe, the Big Bang, and will complement our view on the universe and how we understand it as a human race.
Create a pattern of interference. When a gravitational wave passes through, since it is transversal, it expands.
Pensé que llegaba el profesor, sorry.